Hey guys, welcome to our YouTube channel. So, in earlier videos, we talked about the fundamental forces in nature, in which we discussed about the gravitational force and the electromagnetic force in detail, and we discussed which force dominates at which level, like the electromagnetic force dominates at the atomic or molecular level, while the gravitational force dominates at the terrestrial or celestial level. Now we are going to enter into our third fundamental force, and that is our strong nuclear force or strong forces, we can say. So, as the name suggests, strong nuclear force are those forces which operate at the nuclear level. Okay, so the next question is, how do we know that strong nuclear forces do exist? How do we know the existence of strong nuclear force? So, basically, to understand this problem, we are going to use our basic knowledge of electromagnetic force and the gravitational force, and then we will understand how we conclude that strong nuclear forces do exist. So, in the earlier videos, we talked about the electromagnetic force, the force which exists between any two charged particles, be it positive or negative charged particles. So, in 1911, Ernest Rutherford discovered about the basic structure of atom, which is that there is a central positive core which is called the nucleus, and electron clouds revolve around this nucleus. But in 1970, he discovered that the nucleus consists of protons, which are the positively charged particles, and nucleus can be assumed as a bunch of these small particles which are positively charged. So, as these particles are positively charged, there must be a repulsive force. Here, for example, we are taken a nucleus with two protons. So, there must be a repulsive force which is called the Coulomb force of repulsion. And so, due to this Coulombic repulsive force, the protons try to push each other, and the force magnitude is nearly 20 pounds, which is not negligible. It's quite large value force. So the protons are trying to push each other with that force. So why the protons are not going out? Why the nucleus is still stable? It's intact. So there must be a attractive force between all the nucleons, that is between protons and neutrons, which tries to counteract this Coulombic repulsive force, and the attractive force which tries to bind all these nucleons, that is neutrons and protons, is none other than our strong nuclear force. So now we will study about this strong nuclear force. So now we are going to see some of very important properties of the strong nuclear force. First is, strong nuclear force binds the protons and neutrons within a nucleus, means it is an attractive force which tries to overcome the Coulombic repulsion between the protons and tries to bind all the nucleons together within that small mass. Second is, it is the strongest of all the four fundamental forces in nature, means it's the strongest force in nature. Third is, strong nuclear force is charge independent, means the magnitude of this attractive force between a proton and a proton is equal to that between a proton and neutron, which in turn is equal to that between a neutron and neutron. Fourth important property is that the range of these forces is very small. These are short ranged, and means their effect is only appreciable within a nuclear range, means within 10 to the power minus 15 femtometer range only. Now, fifth property suggests that strong nuclear forces are largely attractive. Largely attractive, yeah, they are attractive, but they can also be repulsive. For example, in the graph shown in this video, you can say from the potential energy versus is the distance of separation graph that there is repulsive as well as attractive force. So what happens is that over a particular range, over a fixed distance, here the fixed distance is nearly 0.8 femtometer, the particle is in stable equilibrium. So after that distance means greater than that 8 femtometer, 0.8 femtometer, the attractive force exists between these nucleons. But when we try to reduce the distance below to 0.8 femtometer, then the force becomes repulsive. So it shows that the strong nuclear force is attractive over a very small distance, means greater than 0.8 femtometer and less than 10 to the power minus 15 meter, which is nearly the nuclear rate. And as we discussed earlier, that strong nuclear force is a short range force, means its value rapidly decreases to zero after a particular distance, and the maximum distance at which this force tends to be attractive is nearly 2.5 to 3 femtometer. After that, the value of this force decreases to nearly zero. The strong nuclear force is also responsible for the radioactivity and nuclear phenomena such as fission and fusion. Let's see how this force affects the radioactivity and nuclear phenomena. But before we enter into that part, we must understand a very important property of nuclear forces, and that is the saturating nature of nuclear force. So, what this saturation of nuclear forces means? It simply means that the value of nuclear force within a nucleus first increases and then it becomes maximum. After that, the value of the attractive nuclear force becomes nearly constant whether the size of nucleus increases or kept on increasing. So, what this suggests? This suggests that as the size of nucleus or the number of nucleons kept on increasing, then after a certain number of nucleons, means protons or neutrons, the nuclear force magnitude, means the attractive force, becomes nearly constant. So, the attractive force becomes nearly constant means this suggests that the nucleons interacts only with the surrounding or the touching nucleons effectively. Other nucleons which are not in touch or which are not in contact with the that nucleon do not contribute in the nuclear force in that much amount. Let us see now how strong nuclear force plays an important role in the radioactivity of heavy nuclei. So, let's see what happens there. As we have discussed now that the strong nuclear force magnitude becomes nearly constant after a certain limit, means as we keep on increasing the number of nucleons, means protons or neutrons, the attractive force becomes nearly constant. But as the number of protons is increasing, the Coulombic interaction, the repulsive force within the nucleus, is increasing. So as we continuously increase the size of nucleus, the Coulombic force, the repulsive force, starts to dominate over the strong nuclear force. So the higher nuclei tends to be unstable, and for due to this instability, the nucleus starts emitting some of the particles like alpha particle, which helps in gaining stability. In actual, radioactive decay is governed by both the strong nuclear force and the weak forces. For example, the strong nuclear force helps in understanding our alpha decay, while the weak nuclear force help in understanding beta positive and beta negative decay. So let's understand now what is a weak nuclear force, which is our fourth and last fundamental force. Weak nuclear forces or weak forces. Weak nuclear forces are encountered when we deal with the reactions involving subatomic particles like protons, neutrons, and electrons. The range of weak nuclear forces is very, very small. It's nearly the size of proton or a neutron, means they are even much small ranged forces than strong nuclear forces. So, the effect of these forces is experienced only when we deal within a proton or a neutron. For example, weak nuclear forces are responsible for the beta positive or the beta negative. We will study about these decays in our nuclear physics, which is a part of 12th course. and we will study it in very detail. In next video we are going to see the relative strengths of these four fundamental forces and their little bit differences and as well as similarities.